We're about to work through some practice problems. Now, for the best effect, you should always try these problems by yourself first. If you're watching this video for the first time, you can use that pause button when you see a problem and try it yourself. Unpause to see if we agree. An alternative is you can follow the links below and you can find a copy of these problems which you can work out at your leisure. All right, let's get going. Find the integral from 0 to pi, 0 to 1, y, sine of xy, dy dx. All right, so we're just integrating. Woohoo! Nice! Now looking at this, our first reaction is, oh, this looks like we might have to do an integration by parts, because we see a y times the sine of xy. That doesn't sound like a fun thing to do. But, you know, we can always switch the order of integration if we think that might be easier. And notice if we integrate with respect to x first, hey, that makes life a little easier. So let's go ahead and switch the order of integration. And because we have nice bounds, these are all numbers, it's pretty easy to update the bounds. So this will be integral, integral. We'll still have the same function. And now we're going to do dx, dy. All right, and our bounds are now going to be y goes from 0 to 1, and x goes 0 to pi. If you don't switch the bounds, you get a different answer. So make sure you do that. Okay, now only one x. Nice. This will make it a lot easier to integrate. And so when we integrate, y is treated like a constant. What's the antiderivative of sine? Negative cosine. All right. So this will be integral 0 to 1 of y times negative cosine of xy, but I have to account for that constant on the inside. So we have to divide by y. And then we're going to evaluate from x equals 0 up to x equals pi, and we're going to then integrate that with respect to y. All right, well, let's see, what does this give us? Well, good news, the y's cancel. Yes. All right, and so what do we have? Well, we have the integral from 0 to 1 of minus cosine pi x, and then when we plug in 0, we're going to get cosine 0, which is 1. And then we're subtracting that minus 1, so that makes it really a plus 1. All right. And great. Good. Good. And whoops, I put an x here. That should be a y. Excuse me about that. Right, because plug in x equals pi, not y equals pi. Check your mistakes. As the great philosophers would say, you should check your work so you don't make a silly mistake. All right, wait, no, that's not what they said, but close enough. All right, what's the integral of cosine pi? Y. Well, the integral of cosine? Sine. And so it'll be a minus sine of pi y. Don't forget to divide by the constant, in this case pi. Integral of 1? Well, y. And now evaluate y equals 0 to y equals 1. When you plug in 1, sine of pi is 0. And then 1 is 1. All right, plug in 0. Sine of 0 is 0. 0 is 0. So our answer is 1. All right. Good. Nice. Now, on a side comment, we're not going to go through and actually look at this, but if you had forgotten to switch the bounds, you wouldn't have gotten 1, you would have gotten pi. And so be careful. You know, just because the answer might match one of yours doesn't mean you didn't make a mistake. And so be methodical. Be methodical. Check your work. Look for small problems. And oftentimes it's the small ones that cause the biggest headaches. And so just there's no prize for finishing 20 minutes early. There's a prize for doing it right. So just take your time. You'll be fine. All right. Nice. Problem done. On to the next one. Which integral finds the surface area of z equals x squared plus x minus 3y over the region x goes from 0 to 1, y goes 0 to 1. Now, from the bounds, we're not going to get any helpful information. They all are 0 to 1, 0 to 1 for x and y. So this is all about what are we integrating. So let's make sure we know what we're asked to find. This is asking us about surface area. All right, good. So in some sense, it's like the integral of 1 dSA. So, all right, but where does that come from? Well, we have a nice generic formula, which says if you're looking for the little piece of surface area over your region, well, that's the square root of 1 plus f sub x, xy squared, plus f sub y, xy squared. All right. So, in essence, we're after this piece. Now, looking, it's probably almost surely not a or b, because those don't have square roots. It's really, really hard to get rid of a square root. About the only time you can get rid of a square root is when you have a very uninteresting case, or maybe very interesting depending on what you want. You can, when can we do it? We can do it for planes, and we can do it for cylinders, even for spheres, and for bowls. There's still square roots that linger. All right, now what is the f here? Well, f is your function that defines your surface. So that's this piece over here, this x squared plus x minus 3y. This is your f of x comma y. So we say, oh, okay, all right, we know where we're going here. So we're going to have here the square root of 1 is 1. Take the derivative with respect to x. 2x plus 1, square it. Take the derivative with respect to y. Negative 3, square it. Okay. Now, that's none of these options, but we can expand it on the inside, because that looks like what they did. And so what do we have? We have square root 1, 2x plus 1 quantity squared. Well, that's a squared, so that's 4x squared, 2ab, 4x, and b squared, and then negative 3 squared would be 9. And, well, we've got some constants, so we can run all together, and we have the square root of 4x squared plus 4x, 1 plus 9, plus 11. And we're like, aha, that's what we're looking for. And so square root's good. 4x squared plus 4x plus 11. So the answer is C. There we go. Nice. So when you're setting up a surface area problem, just remember you have to remember this expression. Square root of 1 plus these partial derivatives squared. And of course, this is not just surface area. This also shows up whenever you're doing surface integrals, unless, of course, you happen to be doing a flux, but that's a different story. But who knows? Maybe we'll get to tell that later on. But for now, we're happy. We got the answer. Nice. Convert the following integral in cylindrical coordinates. And yeah, we see z's, r's, and thetas, feeling very cylinder, to one in spherical coordinates. That should be rhos, phi's, and thetas. Oh, yep, those are all rhos, phi's, and thetas. Okay, so we need to figure out what's going on. And when we think about changing, you always have to make sure you account for three things: your region, your function, and how you break things up. Now, let's make one quick observation, which is the theta. Looking at this, we see, theta is going 0 to 2 pi, and there's no other thetas anywhere else. Now, that tells us something really nice. It tells us we have symmetry around the z-axis. So, in other words, when we think about the shape that's being formed, we're taking what I would call some region in the RZ plane, and we're going to spin it. So, okay, so that's going to help us get a real good handle on what's going on. All right, so we'll come back and explore that in a few minutes. Well, let's see, what else can we say? We should check. Theta is 0 to 2 pi, yeah. Okay, so that doesn't narrow anything down. Okay, so let's do a sketch. Let's look in our RZ plane. So we'll draw some lines here. So we're going to, and so R and Z. Now, looking at what we have, what can we say? Well, we look at our Z part, and we see that Z goes from 2R, so Z equals 2R, so that's a line a little bit steep. So there we go, there's our Z equals 2R. And then the top line, it's something slightly different. It's Z equals square root of 3 plus R squared. Now you might say, wait, what's that? Is that a circle? It feels circle. Well, maybe. Hold on. Let's check. So what can we say? Well, we can do a little bit of side computation here. If Z equals the square root of 3 plus R squared, then if you square both sides, you get Z squared is equal to 3 plus R squared, or Z squared minus R squared equals 3. Oh, minus, that's not a circle. If it was plus, that'd be a circle. Minus indicates something a little different. Well, what does it indicate? Well, it actually indicates it's a hyperbola. We don't need to know the specifics, but what can we do? Well, we just need to know enough to get a sort of an idea. Think about plugging in 0. When you plug in R equals 0, where are we at? We're at root 3. And then think about what happens as you let R get larger. As R gets larger, you get bigger. So you're drifting up. And so we have something that's drifting up. All right, so there is our shape. Now, we can think about what will this look like if we were to spin it. And if you spin this, what do you see? Well, you look like we have a cone here, except what's going to happen is that the top of the cone is not flat. It's like we took a cone, so we have this cone, but we like scooped a little bit out of the top. All right, so that's our basic underlying shape. Now, one important thing for us that we need to figure out is where do they intersect? We really hope they intersect in a very convenient spot. Well, what would be really convenient for us, look at this bound. That is an R equals 1. Let's check. So we didn't mark what that curve was, so we should write it down. So this is our curve Z equals square root of 3 plus R squared. Okay, so plug in R equals 1. 2 times 1, 2. Square root of 3 plus 1, square root of 4, 2. So, good news, when you plug in 1, they both produce the same value of 2. Phew! Good, good. That's great news for us. All right, well, now we have a pretty good idea of what our region will look like. Okay, so let's turn our attention to some other issues. What's our function? What is our thing that we're breaking up? Now, if you look, you might say, something feels off. We're in cylindrical. So when we think of cylindrical, we oftentimes think of it as polar plus z. The reason we do that is it's because it's polar plus z. So there's a good reason for us to think that way. And so when there's polar, there's usually an R involved. There's no R here. What? So how does that happen? What does that mean for us? Well, it means that we need to put it in. And so we're going to add an R. And you might say, are we allowed to do that? And the answer is we are if we're careful. So when we say we're careful, we can add an R, but we also need to make sure that the net effect is the same as before. So we'll divide by R. And now we're going to have two parts. So one part, this R dz dr d theta, this is going to be our dv term, which leaves this other part, namely this z over r. This part is going to be our function. And so now we just need to understand what this will translate into. Okay, so let's go ahead and work those two pieces out. So we have our z over r and our r dz dr d theta. So we need to convert into spherical coordinates. It looks like it probably will be helpful for us if we can figure out what to do with z and r. We know what are they in spherical coordinates. So we'll make some notes here on the side. We know that rho squared is x squared plus y squared plus z squared. We know that z is rho cosine phi, and we know that r is rho sine phi. This is our sort of basic collection of facts for switching into spherical coordinates. So we say, okay, so with that in mind, we can now update. So we say, all right, so z is going to become rho cosine phi. R, rho sine phi. Okay, that's the first part. And then this r dz dr d theta, that's going to become your dv, which in spherical coordinates is rho sine of phi d rho d phi d theta. Yes? Good. Now, let's clean this up. We can do a couple of things. The rho's in the front here, cancel, and the sine cancels. So what's left? Well, we still have a rho squared, but it becomes rho squared cosine of phi. So that's what's going to be on the inside. So that's the function plus how we break things up. So we are looking for this function on the inside. All right, rho squared cosine phi. Yep, that's still a possibility. Rho squared sine of phi. Nope. Rho squared sine of phi. Nope. Rho squared cosine phi. Yeah, that's still a possibility. Rho squared sine of phi. Okay, so we've now narrowed it down to two options. And the good thing is, if we think about it for just a little bit more, we actually have enough to say what our answer is right now. Look at these bounds for D. What is rho going from? Rho goes from 0 to root 3. Well, what is rho equals root 3? If we think about that, I would say, hey, rho equals root 3. This is the sphere of radius 3. Now, thinking about our shape, a sphere of radius 3 would be coming down. Do we have a sphere of radius 3 in our picture? We do not. Okay, so it's not going up to a sphere of radius 3, which means our answer is A. However, that's still somewhat unsatisfying. I really want to understand where these are coming from. So we're going to push on. All right, so what comes next? Let's talk about our bounds. We know our theta bounds, same as before. So let's go to our phi bounds. Where does phi come from? Well, phi, as a reminder, comes from an angle off the positive z-axis. So we have here, we'll put a pointer here. So there's going straight up is phi equals 0. And now, see how we're part of our region? So we're starting at phi equals 0. Turn, 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 stop. That point right there, that's the angle where we finish hitting our region, because after that, we're out of our region. So we're going from phi equals 0, okay, that's good, to this angle here. So now the question is, what is that angle? Well, if we take a look, we see the height here is 2, this side is 1, and we say, that angle would correspond to when the opposite is 1, the adjacent is 2. So that's when tangent of phi is 1 over 2. Or phi would be arctangent of 1/2. So we should go from angle 0, which is straight up, to arctangent of 1/2. That's that line there. That's what phi does. Okay, good. Check. All right. So we check that bound. We check that bound. We've already checked the, check that bound. Check that bound. I was looking at B. I should be looking here. We've already checked the function. All right. So these are eliminated because of functions. Might as well go ahead and say bounds are good. Here, that's no good. And that's no good. Okay. So, all right. Now, the last piece, rho. Well, rho always comes out from the origin and heads in a straight line. So we're coming out from the origin, we're moving out in a straight line. So here we are, we're at 0 until we hit that part. Okay, so the question is, what is this in terms of rho? Well, we already saw a clue. It's z squared minus r squared equals 3. So what does that become? Again, we come back here. That would be rho squared cosine squared minus rho squared sine squared equals 3. So you can factor out a rho squared. You get cosine squared minus sine squared. You say, cosine squared minus sine squared. That sounds familiar. It sounds like the kind of thing that they really drive into us, like it's an important trig identity. And yeah, it is. And so that's cosine 2 phi. Now, I want to get rho by itself, so I need to move the cosine across. We do it by dividing. Dividing by cosine really means multiply by secant. So that gives us rho squared is 3 secant 2 phi. And now if you want rho, take the square root. Rho equals square root of 3 secant 2 phi. Which means that we need to go from 0 to the square root of 3 secant 2 phi. Which, yes, that's the right bound here. And it matches here, but nope. So anyways, a lot of these you can eliminate by various means. You don't have to do the whole thing. Like we kind of knew a couple minutes ago, and you're probably like, why did you keep going? Just to sort of say, look, let's just verify everything. Everything matched, but all the other parts, there was one or maybe multiple parts that didn't line up. And so it's just a matter of saying, okay, think about elimination. That's oftentimes just as useful as doing the whole problem. If you can eliminate all the other options before you reach the end, then you're done. Right? Take advantage of it being multiple choice. But all right, good. Lovely geometry. Who doesn't love a good geometry problem, right? We all do. They're great. When carrying out a change of variables, x equals uv, y equals u squared minus v squared, then dx dy is something du dv. All right, so we're talking about change of variables. And the good news is we're not doing the whole problem. And so let's just pause for a second and say, when we're doing the whole problem, we're really saying there's 3 things that have to be done. Because every integral involves 3 parts. There's the region you're integrating over, the function you're integrating, and how you're breaking things up. We are in the how you're breaking things up phase. And in some sense, this can be a little bit subtle. I mean, every piece has its own subtlety. And in particular, what are we looking at? Well, this comes down to understanding the Jacobian. So this is a problem about the Jacobian. All right, so let's think about what's going on. we're changing our coordinate system, and as a result, we have to capture sort of local expansion or contraction. And that's what the Jacobian is doing. And the way we do it is we look at the partial derivatives, because it's telling us how things are changing as we change our variables. So since we have x and y in terms of u and v, then we would do the following. We're going to take a 2 by 2 determinant. So we're going to have derivative of x with respect to u, derivative of x with respect to v, the derivative of y with respect to u, the derivative of y with respect to v. And the nice thing about the Jacobian is it's very forgiving. The Jacobian forgives all. In other words, if I accidentally put the columns in the wrong order, or what I put as columns I put as rows, it's still going to give the same answer at the end of the process. So that's why this is a very nice problem. So let's take our partial derivatives. The derivative of x with respect to u is v. The derivative of x with respect to v is u. The derivative of y with respect to u is 2u. The derivative of y with respect to v minus 2v. All right, so it's this 2 by 2 determinant we need to compute. So we're going to go down the diagonals, up the other diagonal, so down the diagonal, minus 2v squared. Up the other diagonal is going to be 2u squared, but we subtract. All right, so we've taken our determinant, and now the other thing is this: we want to measure expansion contraction. We want to talk about it as a quantity. It's a measurement quantity. We want a non-negative number. So we take the absolute value, and what do we get? Well, we get 2 times u squared plus v squared. Now, how do we interpret this? Well, what this tells us is if we're switching from x and y, when we take our Jacobian, this is a function u and v, and it really says that dx dy is this expression here, 2 u squared plus v squared du dv. And now we check, is that one of our options? It is, and we're done. Okay, so the answer is D. Good, good. Now, we're done with the problem, but I will say it is possible that perhaps the instructor was having not the happiest day, and they said, let's change the question. Same substitution. X equals uv, y equals u squared minus v squared. But now, I want to know the answer to the question, du dv equals what dx dy? What goes in the box? Now, your initial reaction should be, well, that's not so hard. You just divide. That's correct. We just divide. However, there's a small caveat. Well, when we divide, we end up with u's and v's here. We want x's and y's. So what do you have to do if you had this problem? Well, you try to think, how can I take the expressions u squared minus v squared and uv and write u squared plus v squared? Well, it's going to be a little bit tricky because of the minus there. It's almost like y, right? So if you do a couple of observations, and again, because this is not part of the problem, I'm going to not hum and haw too much. Suppose you look at y squared. That's u squared minus v squared squared. And, well, that's u to the fourth minus 2 u squared v squared plus v to the fourth. Okay, all right, that's a true statement. Well, if you go a little bit further, you can say, well, hey, you know what? This is u to the fourth plus 2u squared v squared plus v to the fourth. And I go, well, yeah, of course, it is that. But why do you bring that up? Minus, oh, wait, yeah, we need one other piece, right? Plus 2 minus 4u squared v squared. And what do you have? You have u squared plus v squared squared. And here you have minus 4uv squared, or if you look at that, that's u squared plus v squared squared minus 4x squared. All right, move it across. We get that u squared plus v squared squared is equal to 4x squared plus y squared. Or, last thing, taking a square root, u squared plus v squared is the square root of 4x squared plus y squared. All right, so, yes, it is true we would just divide, but then we'd have to convert. So what we'd end up putting here is we would replace the u squared plus v squared as 2 square root 4x squared plus y squared. But the good news is, that's not what they asked. Oh, thank goodness. Thank goodness. And but I just want to say that possibility does exist, and sometimes people do ask it that way. And so the good news is we have loving, gentle teachers here. They give us like a warm embrace. Can you feel the love in calculus? Yes. All right, let's stop working on this problem because we have more problems to do. We're asked to take the div, which is short for divergence, of this vector-valued function. All right, now what is the divergence? So divergence is, it's applying that del operator, sometimes you call it nabla. So the divergence of a vector-valued function f is equal to del dot f. So it's the dot product one. And in particular, we say, well, if we're thinking of it as m and p, remember that this is the collection of partial derivatives. So what we end up with is partial m, partial x, plus partial n, partial y, plus partial p, partial z. So when you take the divergence, you start with the vector-valued function, you end up with a scalar. So there's no vectors involved. Look at D and E. Vectors. No. That's not possible. So understanding what the divergence is helps us rule things out. On a side note, you might say, hey, isn't E like the curl? Oh yeah. They'll throw in things like that just in case you aren't paying attention. But we're paying attention. We got our eyes on them. All right, so what do? Well, in our case, we say go through term by term. We say, all right, take the derivative with respect to x of x cubed plus cosine y squared. All right, what do we see? Well, this is going to, from this part, 3x squared. And now, well, there's both terms have a 3x squared. And then derivative with respect to y. 4y e to the z plus x squared z. Well, this part is going to be 4e to the z. You might say, well, wait, what's happening to this cosine y squared? What's happening to this x squared z? They're constants. See, the nice thing about this, the divergence, is a lot of terms disappear because we have lots of terms which don't depend on the variable we're taking the derivative with respect to. So the last part we get is minus 1. So we're looking for 3x squared plus 4e to the z minus 1. So even though, yes, this has pieces of that, this has a lot of extra stuff that shouldn't be there. So the answer here is A. And there you go. So the divergence, that's a fun one. You just start looking at the partial derivatives. And oftentimes, after one or two partial derivatives, you're like, oh, I see only this option has what I want. I don't even have to really worry about the rest. And so, yeah, divergence. Haha, who knew? It could be fun. which integral finds the inertia with respect to the x-axis for the region described in polar coordinates by theta goes 0 to pi and r goes 0 to theta. Now, if you're panicking about the bounds, notice that all the bounds match. So this is not a bounds question. It's about what's on the inside. So we have all these little pieces here floating around. All right, so we need to think about what we are doing. We're integrating and we're trying to find inertia. So this is one of our measurements, things we might find, right? Because there were three things. There was the mass, moment, inertia. And so we can be asked for any one of those. So we want to make sure we're ready to answer any of those. So what's the difference? Well, it comes down to distance. Mass, you don't care distance at all. Moment, you care about distance. Inertia is distance squared. So in particular, when we talk about inertia, what we're going to have is an integral over our region of our distance squared, our density, and then our bit of area. And circularly what's happening is that our density times a little bit of area this is a little tiny piece of mass. So it's really mass times distance squared is how you find the inertia. All right, when we're thinking about inertia or moment for that matter, we have a distance. You always think about distance with respect to what? Well, so let's sketch. We don't need to know what our region looks like. It looks something like this. This is the curve r equals theta from 0 to 2 pi. And so, sorry, from 0 to pi, not 0 to 2 pi. And so when we're thinking, we're saying, hey, we want to do with respect to the x-axis. Well, that says take your little tiny piece and go down to the x-axis. How far away is that axis? What's your distance down to the x-axis? And you're probably thinking, why? Well, because we need to know. Oh, you were thinking the variable y. I'm so sorry about that. Sorry. Sometimes, it's hard for me to mind read, and things get a little bit cloudy. Yes, it's y. Y is how far down you go to get to the x-axis. So what do we have? In our case, we have our integral over our region, and then our distance squared will be y squared, and our density is the square root of x squared plus y squared. All right, so that is what we have if we wrote it in terms of x and y, but we need to write it in terms of polar because everything's set up in terms of polar, right? The region is in terms of polar, and the integrals are in terms of polar. So we have integral, and they already were very nice. They gave us our bounds, so we don't need to stress about that. We'll just copy them again. 0 pi, 0 theta. Now, in polar, what is x? Well, remember we have our basic facts. X squared plus y squared equals r squared. X is r cosine theta, and y is r sine theta. So we have our basic facts, and no surprise, we see a bunch of signs here. So that, y will be r sine theta, so it's r sine theta squared. Square root of x squared plus y squared. Well, that's r, right? If x squared plus y squared is r squared, square root of x squared plus y squared is r. And dA, that is r dr d theta. Okay, so we really have three things in play, right? We have the y squared, the square root of x squared plus y squared, the dA. Now, when we put all of these pieces together, well, what do we have? Well, let's count our r's. 1, 2, so 2, 3, 4. We need an r to the fourth, sine squared. Sine squared, and dr d theta. Okay, so we're looking for, because the bounds match, the dr d thetas match, we want r to the fourth and a sine squared. All right, so the sine squared, good, but that's wrong. R to the fourth sine squared, yes. This is wrong power of r. The sine squared is good. Wrong on both counts, yes, but no. So, okay, so it is in fact B. All right, good, nice. Now, if we had confused moment with inertia, so we only had distance, you might notice that our answer would have been r cubed sine theta. So the moment with respect to the x-axis is one of the options. So make sure you keep things straight. Mass, no distance. Moment, distance. Inertia, distance squared. So you need to square it. But all right, once you have it and you understand, well, life is not so bad. It can actually be pretty decent, right? Yeah. Change the order of integration for, we're going from 0 to 1, z minus 1 to 1 minus z, minus root 1 minus z to plus root 1 minus z, f of x, y, z, dx, dy, dz, to dy, dz, dx. Oh, okay. So we're changing order of integration. Okay, well, this is going to be interesting, right? So what do? Well, there's sort of a process we go through when we're changing order of integration. And no, the first step is not have a mild panic attack. And if you are, stressing, always remember, breathe in, breathe out. In, out. Be calm. We got this. We can do this. But now, once we've oxygenated ourselves through our deep breathing, where do we go? Well, we're going to start by saying, what are our current bounds? So let's go ahead and figure that out. And remember, the bounds are being stored in our integral signs. So we have our relationships. So our outer layer tells us that z is currently going from 0 up to 1. And now the next layer tells us about y. It tells us we go from z minus 1 less than or equal to y less than or equal to 1 minus z. Now, let's just pause here before we go into our innermost layer, because if we think about it, the outermost number to number and the innermost curve to curve. Now, number to number, we know what that looks like. It's just like line segment. So the outer two, that gets us a pretty good idea of what's going on in sort of 2 dimensions. So let's think about that. So we're going in y and z. So we'll just sort of think here for the moment. We'll mark y and z. Now, what do we know about z? We're going from 0 up to 1. So there's 1. Now we have curves. And one curve is y equals 1 minus z. Another curve is y equals z minus 1. Now, because the way we're drawing this, it may not be quite so quick, but that's okay. We can rewrite this. So we have y equals z minus 1. Or if we rearrange, we could say that this is the same as z equals y plus 1. And so what does that look like? Well, we hit the y-axis at 1, and we have a slope of 1. So we have a slope of positive 1. All right, so here, this is our line, z equals y plus 1. All right, great. Now the other side, that was our y equals 1 minus z, or we can move this around. This is the same as z equals 1 minus y. So we hit the we hit the z-axis at 1, but we have a slope of minus 1. So we look like that. All right, great. So we have this other line, z equals 1 minus y. And what's true? Well, we're going in between, left to right. So we have our nice triangle here. Okay, so there we go. In terms of the YZ, we have a triangle shape. Now, we have to go up one more level. And now we come up to our X. So, X, we're told, goes from minus square root 1 minus z to plus square root 1 minus z. Now, this is a surface, but let's see if we can't think about what the surface is. So, in both cases, usually we like to think of our surfaces as z equals. Not because there's anything sacred about that, but more because of that's sort of how we've been programmed, right? We think of y as functions of x. We think of z as functions of x and y. So square both sides, and let's try to solve for z. When we square both sides, you get 1 minus z equals x squared. Over here, you get x squared equals 1 minus z. Like, oh, these are the same surface. We're just sort of capturing two halves. And in particular, if you look, you say, it's really the surface z equals 1 minus x squared. All right, so let's see if we can understand what's going on. And now, of course, is the dangerous part where we're trying to draw things in 3 dimensions. But, all right, we'll try to do the best we can. We have our x, our y, and our z. Now, this portion, that's going to come into play. So I am going to mark it really quickly. We have 1 minus 1 plus 1. So we have this triangle. And so that's the region we're going to be integrating. In other words, if we were to look down the x-axis, our shape would look like that triangle. Now, we have this other shape, which is z equals 1 minus x squared. Well, what does that look like? Well, in the zx plane, if there were no, in other words, we weren't actually thinking this in terms of 3 dimensions, we were thinking this in terms of 2 dimensions, it would look like an upside down parabola. Because, well, it's an upside down parabola. That's why we would think of it that way. And so that's what it is in 3-dimensional space. So what we have is this upside down parabola, except what's going to happen? Well, we're going to copy this parabola in all directions, back and forth. So that as we move our y, we always get our same value for the parabola. It's always the same shape. Okay, so now, moment of truth. What is our shape? What does it look like? Can we figure it out enough? Well, what's going to happen is we're just think about, now look down the x-axis. We're only going to keep the part that we'd see if we looked at that triangle portion. So we would see this part. We have our base here, and then we're going to come up and come back down on this side. And then on the other side, we'd do something very similar, where we would come down, and then we would come down to the other side. And it's a little hard to see, but looking down the x-axis, that's what we see. What would we see if we were looking down the y-axis? Because that's what we need to figure out. Well, if we look down the y-axis, what we're seeing are a glimpse, and I probably have my shape a bit wrong here, but what we would be seeing is we would be seeing this parabola. Okay, so down the y-axis, we're going to keep our parabola. So it's going to be, actually, it's going to look at the same picture. I don't know why I redrew it. It's this shape. It's the z equals 1 minus x squared. Okay, so that's the shape that you see down the y-axis. All right, so how do we get our answer? Well, the good news, we know we're going dy dz dx. That's why I wanted to look down the y-axis. When I look here, I ask the question, well, as I move in the y direction, which surfaces are we going to move between? So we're going to be moving in the y direction, right? We're moving this way, back and forth in the y direction. And what's our surface? Well, we're going to hit one side of our triangle and move across to the other side of our triangle. So in other words, we're really moving back and forth in this way. So we're moving from our flat triangle face on one side to our other flat triangle face. I say triangle, but it's really more curved. But okay, so we're moving from this flat face to this flat face. All right, so for our integral, we have integral, 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 f of x, y, z. Our order is dy, dz, dx. So flat face to flat face. So we're going from these faces here. So we're going to go from the back end for y. That's going to be the plane z equals y plus 1. So I need to solve for y because I need y equals. So that becomes y equals z minus 1 to the front face. And so low values of y to higher values of y. So that's z equals 1 minus y. And okay, so that goes to y equals 1 minus z. So we're going from z minus 1 up to 1 minus z. All right, so that's that layer. Now, where is z going to go from, and where is x going to go from? Well, once the inner layer is done, we look down the axis and say, we have this lovely picture. We see where we are hitting the x-axis. We're hitting at -1 and +1. So we say, well, that tells us that x goes -1 to 1. So -1 to 1. And then for any value of x, we go up and we say, hey, we're going from 0 to the parabola, 1 minus x squared. And we're done, because we were asked to change the order of integration, so it's really just a matter of changing the bounds. And so there we go. Now, oftentimes the biggest challenge that people have with these types of questions is like, how do I get the picture? Because even me, looking at this picture, I was like, I think I slightly messed it up. And that's because I think I slightly messed it up. But the thing is, you don't have to be perfect. You just have to get enough to get some intuition. Think about the surfaces involved. How are things interacting? Ultimately, at the end of the day, it's trying to understand what bounds your shape. So when we look at this, we say, well, we have a couple of things bounding it, because we see there's a triangle shape, and so that corresponds to two flat planes, right? We have a flat plane on this side, a flat plane on that side. Then we also have this. If you think about it, it's like you took a flat piece of paper and then sort of folded it, right? So you have a folded sheet, a parabola, and it's this parabola going back and forth. Well, that's going to give you more bounds, right? But that gives you more bounds in sort of the XY direction. And that helps you understand what's going on. And so just think about what are your bounding pieces. And once you have that, think about, okay, now how do I get my new bounds? Think about when you move back and forth, what bounding pieces do you hit? That gives you your inner layer. Look down your axis. In this case, look down the y-axis. You have a 2D picture, and then you can get your outer two layers. Now, here's the thing. we're not trying to make it impossible. I know sometimes it feels that way. I am confident that your instructors like you enough that they will give you a picture if it will help. So don't panic and be like, oh my gosh, I don't know what's going on. So even though I didn't give a picture, that's because I like to give ourselves a good challenge, And but that's okay. They'll be nicer. They're kind people. They're very nice people. I've even had meals with these people, so they're nice. All right. Anyways, that was a good problem. We still have a couple more, right? So let's finish up the last couple. Let C be the curve parameterized for 0 to 1 by r of t is t squared plus 2t, t e to the t minus t squared, 1 minus cosine pi t. Find the integral of C of this y minus z squared x plus 2y, 3z squared minus 2x dot dr. All right. Now, this is one of the things where we have like so many notations for the same thing that it gets really, really annoying. So this dot dr, you should really think of this as your dx, dy, dz. So a better way for us to write this is the integral along our curve of y minus z squared dx plus x plus 2y dy plus 3z squared minus 2xz dz. All right. So that's a better notation in some sense, because I think it gives a better idea of how we're going to approach this. Now, there's a couple of clues about what we should do. And usually the biggest clue is you look for things which are really like, messy. It's like, these look like terrible terms. And you'd never want to do a line integral with that parameterization if you had to actually do like a ds kind of argument, because it would be hopeless. And that's the whole point. We want you to be like, I don't want to actually do the integral in the way it's written. We don't want you to do that either, because that makes it harder for us to grade. Oh my gosh, do you know how many pages that would take? So what are we doing here? We're saying, do you recognize the tools? Say, okay, well, it's a line integral on a curve, and it's one that I say would have orientation, right? And somehow the way you go matters. So there's this nice thing, the fundamental theorem of line integrals, or if you like, the fundamental theorem of calculus for line integrals. And that would say one type of line integral is really easy. So recall, we have, I'll write it down here. This is the fundamental theorem of calculus for line integrals. And we get the following, namely that the integral along the curve of the gradient of f dot dr, so just using their notation, I'll borrow their notation, well, that's equal to the function evaluated. You plug in the stop and subtract, plug in the start. It's plugging at the end minus plugging at the beginning. All right, so there we go. That's it. So if we have the case where this is the gradient of something, or in other words, gradient of f means we're a conservative. Okay, so that's another way to just phrase this. Then we are golden. So that says, hey, we have here this f. This is, by the way, the potential function. And essentially it's like acting like the antiderivative. So we're coming to this fingers crossed and being like, they like us and we like them. Let's see if this is a conservative line integral. So then the problem really boils down to, what's the potential? What are the endpoints? So before we worry about endpoints, let's see if we can actually use the theory. So our goal, try to find an f. All right, so now that's our intermediate goal. Try to find our potential. And isn't that what college is all about? finding our potential. Wait, no, that's a different kind of potential. All right, potential function. Okay, so here we go. What's the idea? If indeed there is a potential function, what we really have given here are a series of partial derivatives. Derivative with respect to x, derivative with respect to y, and the derivative with respect to z. And what we need to do is to somehow reassemble and put together what would be our function. So we're going to do that by taking integrals of each piece with respect to the variable and say, hey, do we have compatibility? And if we do, how does it all fit together? So we'll take the integral of y minus z squared dx, which means that we're going to treat x as our variable, so y and z squared are constants. So this becomes xy minus xz squared plus some constant function, I'll call it d, which only depends on y and z. And we're going to do that with each step here. All right, integral of x plus 2y with respect to y. That would be xy plus y squared plus some function which only depends on x and z. And then our last piece, we have our integral of 3z squared minus 2xz dz. See how it's like it tells you what to do? Integrate the part with the dx, integrate with respect to x. With the dy, integrate with respect to y. With the dz, integrate with respect to z. It just feels right. You know, good notation is wonderful. So z is our variable, x is a constant, so that would be a z cubed, and then minus xz squared. Okay, so moment of truth. We are going to check for consistency. We say, all right, well, if we want to put all of these together, what would our function have? And we say, well, okay, I see here an xy piece. It has multiple variables involved, x and y, so I check, is there also an xy? And there is, so that's good. It makes the cut. And is there this other piece, minus xz squared? Again, multiple variables involved. Come down here, there's a minus xz squared. Good. Consistency is paramount. If there was inconsistency, we would have to abandon this approach. All right, I see a y squared, and it only involves y, so that's fine. I don't need to worry about consistency. I'm going to have to compare it to itself. I see a z cubed, and again, I just have to compare it to itself, and that's fine. So I add that in, and now I could add an arbitrary constant, but I don't need to. Everything's accounted for. Everything's consistent. We are conservative. Woohoo! Yes! All right. And now, are we done? Well, almost. We've in some sense done the hard part. We've done the integration, but we still need to do the evaluation. So let's come back to our curve. We need to find our start and our stop. And so we stop at time t equals 1. Plug in 1. 1 plus 2 is 3. 1 times e to the 0 is 1, because e to the 0 is 1. 1 minus cosine of pi. Cosine of pi is minus 1. So 1 minus minus 1 is 2. Where do we start? Okay, well, we start at time t equals 0. 0 plus 0 is 0. 0 times e to the 0, 0. 1 minus cosine of 0. Cosine of 0 is 1. 1 minus 1 is 0. Okay, so all of this is to say that we now take this and we say, lo and behold, this is going to be equal to our xy minus xz squared plus y squared plus z cubed, evaluated from 0, 0, 0, where we start on our curve, to 3, 1, 2. And the thing is, we don't care about the curve. That's the beautiful thing. This says it doesn't matter what the curve is. It just matters where the endpoints are. Oh, nice. And also nice, lots of zeros. So we only have to plug in the top. So be careful here. Make sure you plug the right value in for the right number. So x is 3, y is 1. So that's 3 times 1 is 3. X is 3, y is 2. 3 times 2 squared, that's 12. So minus 12. Y is 1. So that would be a plus 1. And z is 2. So that's 2 cubed. That's a plus 8. And so we have 3 minus 12 plus 1 plus 8, which gives us a grand total of 0. Ha-ha! Wait, what? Okay, well, yeah, 0 is a perfectly fine number. It's one of our favorite two numbers, 0 and 1. So, yeah, that's great. We did it. We did it. So we found our potential. We found our endpoints. Don't forget to check your endpoints. Make sure you take them in the right order. In this case, it doesn't really matter, but plug them in, and you're good to go. So, okay, good. These are kind of fun. Let's hope for some of these problems on the test, right? We can always hope. Let C be the closed curve that starts at 0, 0. Oh, there's a lot of words here. So let's actually follow this story along. All right, so we have C is a closed curve that starts at 0, 0. So that's the origin. So we have an origin story. And who doesn't like a good origin story? Moves in a straight line to 1, 1. So we move up here to this point, 1, 1. Then again moves in a straight line to 0, 1. So that's x equals 0, y equals 1. So then we move across to 0, 1. And then returning in a straight line to 0, 0. So it's like a triangle. Cool. Okay, so there we go. We have our closed curve. And now the question, compute the following line integral. The integral along that curve C, and this little circle that you see here, this little halo, doesn't mean it's like been an integral that's been sainted. It just means this is an integral on a closed curve. And boy, they're really emphasizing that, right? They keep saying closed curve, closed curve. They're trying to drive home closed curve. And so now what do we need to integrate? 2x minus y e to the 2x minus x squared, x cosine y squared minus 3y dot t ds. All right. Now, what's the idea here? When you see a closed curve in the plane, you think to yourself, hey, if I see closed curve in the plane, Green's theorem. So we're going to think about saying, let's not just do this line integral because that looks like it could be annoying. Now, it's probably not too bad as line integrals go, but it doesn't look too great either. So we'd like to try to avoid having to do anything terribly messy. And you say, okay, so how does Green's theorem work? Well, if you have a closed curve around a region with proper orientation. So remember the rule. To the left, to the left. When you walk the curve, keep the region to your left. Good. So we are oriented the correct way. Then, if you have an integral of the form, m dx and dy. Now, you might say, well, wait, is that what we have? This dot t ds is really dx dy. So we can write this as the integral along our closed curve C of 2x minus y e to the 2x minus x squared dx, and then plus x cosine y squared minus 3y dy. Okay, so we are in the right form. And so Green's theorem says, and we'll put it over here, Green's theorem. And it's the following. So the integral along our closed curve C, m dx plus n dy is equal to the integral over our region of n sub x minus m sub y. Now, the thing here is, why is this useful? Well, it can be useful because when we integrate over a region, oftentimes it's a simpler integral to deal with, and because we take these derivatives, sometimes things which are maybe not nice to look at, go away. Yes, that's the dream. Well, let's try it out. Let's see what happens here. All right, so this looks like we have the integral over our region of, so here, this is our n. So we're going to make some notes here. This is our n, and this is our m. N sub x. There's only one x. That makes it really easy to take a derivative. Cosine of y squared. Oh, wait, what? We're going to integrate cosine y squared? That's crazy. But don't worry, we have this other part. Maybe that'll make it easier. So then we're going to subtract m sub y. Well, there's only one y, so that's pretty easy to derive too. Minus e to the 2x minus x squared. Wait, what? Really? What? Well, at least we can add. So how do we do those integrals? Well, the challenge is, I don't want to integrate that with respect to y. That looks terrible. Maybe I can integrate with respect to x first. Okay, maybe, and then there's some hope. But on the other hand, I don't want to integrate that with respect to x. Hopeless. But maybe I can integrate it with respect to y. You know what we can do? This is cool. So I'm going to make an observation here. Do you see this plus sign? What does that plus sign say? Well, when you have things being added, you can actually separate them. So you can pull things apart into separate integrals. And when we look at this part, it's like, you know, if we were going to integrate this, we should first try to integrate with respect to x. Here, if we're going to integrate, we should first try to integrate with respect to y. Well, those are saying do different things. That's okay. The plus says pull them into separate integrals, and on each one, you can do a separate thing. Because once you've put them into their own sandboxes, ooh, that sounds like a very, very techie term. We're sandboxing them, right? We separate them. Each one has their own sandbox. They can play and do whatever they want. They can approach the problem in different ways. So let's figure out what's going to go on. So we're going to do integral, cosine y squared, and here dx dy, plus integral e to the 2x minus x squared, but now dy dx. So let's think of our region. Well, here, where does y go from? Well, y goes from 0 to 1. So 0 to 1. Where does x go from? Well, given a value for y, we go from 0 out to this curve. Now this curve is y equals x, or if you like, x equals y. And so we go from 0 out to x equals y, so 0 to y. Now here, well, where does x go from? We go 0 to 1. Where does y go from? Well, given an x value, we go from the curve up to there. So we go from y equals x up to y equals 1. Okay. Well, let's go ahead. We'll carry out these integrals. So we have our first round. This will be cosine y squared x, because we're integrating with respect to x, so that's all a constant. Evaluate from x equals 0 to x equals y, dy, plus over here, integral 0 to 1. Now here we'll have e to the 2x minus x squared y, because we're integrating with respect to y, that's a constant. Evaluate y equals x to y equals 1 dx. All right, so this becomes, so secretly, it looked like a Green's theorem problem, and it is, but it's now become a setting up bounds for a 2D problem, and we have to be like, oh, order of integration matters, pay attention. So isn't it fun how we can like merge ideas together? It is. It's a blast. All right. So we have, this becomes integral 0 to 1 of, when we plug this in, when we plug in 0, you get 0. Plug in y, you get y. So it's cosine y squared y dy plus integral 0 to 1 of e to the 2x minus x squared, and then plug in 1 minus x dx. Okay, so we're going to do some substitutions. So with the first integral, we'll let u equal y squared. So then du is 2y dy. We'll move the 2 across, so 1/2 du equals y dy. On the second one, we'll do a substitution. We'll go v is 2x minus x squared. Then dv is 2 minus 2x dx, or 1/2 dv is 1 minus x dx. It's almost like it was planned to work, because it was. Okay. All right. Now, let's not get too excited there, right? We still have problem left to do. So this becomes first integral, 0 to 1 of 1/2, y dy has a 1/2, cosine of u du, plus integral 0 to 1. Now, why is it 0 to 1? 0 squared is 0, 1 squared is 1. Why is this 0 to 1? 2 times 0 minus 0 is 0. 2 times 1 minus 1 is 1. So we're not being lazy in copying the bounds. We're checking, right? So be careful. And, okay, so the 1 minus x dx puts a 1/2, and we get e to the v dv. Okay, so we're almost done with the problem, which is good because we're really running short on space, but that's all right. The end is near. The end is near. Integral of cosine, sine. So we have 1/2 sine of u. We're going to evaluate that from 0 to 1, plus 1/2 e to the v, and we're going to evaluate that from 0 to 1. So when we plug this in, we're going to get 1/2 sine of 1, which is sine of 1. Not much we can do with that. Sine of 0 is 0, so that's gone. Don't have to worry about that. Then we plug in 1 into e to the v, we get 1/2 times e. And when we plug in 0, well, e to the 0 is 1, and then so minus 1/2. So there we go. 1/2 sine of 1 plus 1/2 times e minus 1/2. If you really wanted to, you could factor out the halves and say sine of 1 plus e minus 1. But, that's the same thing, just factoring out the half. All right. Good. It's fun, right? Seeing how all these ideas blend together. Because, yeah, sure, you have a Green's theorem which turns it into a 2D problem. But once you turn that into a 2D problem, you still have a 2D problem. And sometimes you might say, well, what's the right order of integration? Sometimes you might say, oh, let me use polar. They love polar, by the way. I don't know why, but they love polar in Green's. But just think about, I've translated from one problem to a new problem, and now reset and start again, right? And oftentimes, that's how solving problems works. You just sort of move along the line from one idea to another idea, and eventually you get the whole thing. All right, good. Let G be the surface z equals xy over the region x greater than or equal to 0, y greater than or equal to 0, and x squared plus y squared less than or equal to 4 with downward pointing normals n. Find the integral on g. So remember, g is a surface, so this is a surface integral. So we get to do surface integrals. Woohoo! Yes! Okay, all right. Oh, wait, hold on. Let's hold our enthusiasm back. Let's see where this is going. And we're finding y cubed I plus x cubed j minus 2z squared k dot n dsa. SA is short for surface area, right? Because we're doing a surface integral. So the idea is break our surface up into lots of little tiny pieces, figure out what's happening on each piece, and add it all up. Now, what is this? Well, what's being measured here is, if you think of this as a vector-valued function, because it is a vector-valued function, so that's why it's pretty easy to think of it that way. So we really have an integral of g of f dot n dsa. All right, well, what is this? It's the flux, which is just another way of saying the flow of our vector field f through our surface g. And all right, so this really is asking us to compute a flux or a flow through a surface. And we say, okay, well, how do we do that? Well, we're just going to do a surface integral. Now, a lot of surface integrals can get messy because this dsa term, you might recall that has like a square root of 1 plus fx squared plus fy squared, like, but so does the n. And so when you actually compute the flux, it simplifies tremendously. And so there's this nice general setup. So let's talk about our general setup. Okay, so here's the generic formula. So given g, which is, and we have to write what is g, it's the function z equals f of xy over a region R in the plane, because the way we do surface integrals is, yeah, you have the surface up here doing its surface thing. We're going to say, hey, take that surface and push it down into the plane back where we're comfortable doing two-dimensional integrals. So up here, it's like, this does not feel comfortable. Down here, it's like, this feels very comfortable. I like this kind of integral. So we're going to push it down. So we're pushing it down to our region R. So given g, which is of the form some function of x and y over a region R with upward normals, then what we have is that the integral along g of a vector-valued function m and p dot n dsa is equal to the integral over our region. See, this is when we talk about we're pushing down into our region of minus mfx minus nfy plus p dA. Okay, so this is the generic way to compute our flow through a surface. And notice no square roots to be seen, unless mn and p happen to have them, or maybe f and y, f sub x and f sub y happen to have them. But great. Now, how is this working? Well, essentially what it boils down to is that this NDSA, if you work it out, is really this minus fx minus fy1. Now, you may have already noticed something that makes you say, uh-oh. Notice our formula, this thing we wrote down, has a key word which doesn't seem compatible with our problem. This says upward. This one says downward. What does that mean? Well, it means we're going in the wrong direction. The orientation's the wrong way. So our normals are going down, not up. Can we still use this? Yes, but we need to correct for it. So what happens when your orientation's wrong? You fix it by adding a minus. So minus is orientation. So plus and minus, this thing you've thought about since you were very young, it's all about orientation. That's the whole deal. Like, what? They should have told me that back 20 years ago. But now you know. So good. And with great power comes great responsibility. Okay, so here we go. We know what our function is. So we're going to first figure out what we're integrating, and then we'll talk about our region. So our z equals f of xy is xy. So this says the integral over our surface g of, and we can write this, if you like, as y cubed comma x cubed comma minus 2z squared dot n dsa will be equal to the integral over our region of, well, first off, minus, and we're going to make a quick note. This is to fix the orientation. And so minus, then we're going to take our m. We have a minus our m, y cubed, times f sub x. All right, what's the derivative of this function with respect to x? Why? Well, I'm asking because we need to... Oh, you meant the variable y. I can't believe I did that again. I am so sorry. You're right, it is y. Okay, good. I won't make that mistake. Okay. All right, now, that's this piece. Minus n x cubed times f sub y. What's the derivative of the function with respect to y? Yeah, it's x. Okay, plus p. So plus minus 2z squared dA. Now, there's an issue here. That can't be a z because we need to be all in terms of x and y. All the z's have to be gone. So what do? We say, be gone, z! Be gone from our presence! Whoa! Well, no, we don't, there's no witchcraft involved. We use a relationship. We say, hey, look, z equals xy. We can throw that into there. Okay, so let's see what we have. What is this becoming? So this is equal to, everything has a minus, so that's cool. That means the minuses all cancel out. So this is the integral over our region. Y cubed times y is y to the fourth. X cubed times x is x to the fourth. Plus 2. And if we square that, that's x squared, y squared, right? That's our z squared. And we look at that and say, well, that's actually kind of nice. We could rewrite this. This is our integral over our region. If we change the order, this is x to the fourth plus 2x squared plus y to the fourth. Now, does that ring any bells? It is x squared plus y squared squared. Aha. Okay, all right, that's looking pretty respectable. And we see an x squared plus y squared, and we're like, what? Is this another polar? I suspect. Let's talk about now our region. Okay, so our region, we had these three pieces. X and y are both positive. That means we're in the first quadrant. Okay. And now this last piece, x squared plus y squared less than or equal to 4. Well, that's the circle of radius 2. So you go out 2, you draw a quarter circle, and you say, okay, here's our region R. And great, this is perfect for polar, right? Our region has a nice description in terms of polar. Our function has a nice description in terms of polar. Everything's coming up polar. All right, so we're almost done. Well, so what does this become? This is now equal to, switching to polar, integral, we'll figure that out in a second, x squared plus y squared is r squared. So we have r squared squared. dA is r dr d theta. And then theta, well, we start at 0 and we go to pi halves. Right? We're just in the first quadrant, so we don't go all the way around. 0 to pi halves. And then for r, well, we start at the origin and we go out to the circle radius 2. So r goes 0 to 2. Okay, well, we can split that up into two pieces, namely the integral of the theta part, 0 to pi halves d theta, and the integral of the r part, integral 0 to 2 of r squared squared is r to the 4th times r makes r to the 5th. All right, and now what? Well, the first part, that's pretty quick to do that integral. That's theta from 0 to pi over 2, so that's just pi over 2. And then times r to the 5th, integral of that will be r to the 6 times a 1 over 6. And then we're going to evaluate from 0 to 2. Well, if you plug in 0, you get 0. And so you really have what? Pi over 2 times 1 over 6 times 2 to the 6. Well, I have some 2's, right? Because the 6 is really 3 times 2. I can pull off 2 2's and cancel. And so 2 to the 4th makes 16. Don't forget about the 3 downstairs. So this leaves us with 16 over 3 times pi. And we're done. Whoa! Woohoo! We did it! We found our flow. We found it. And that was our last problem. And this was good, right? We turned it, we pushed it down, and we said, hey, this becomes an integral, which is not bad in polar. And so then we pulled out and did the polar computation. Nice. Woohoo! Yes! All right. Well, thank you for hanging in and working through these problems. I hope that you're getting the hang of these. The more you do, the simpler it gets. You know, we all start somewhere. You know, I struggled. You know, I did terrible in algebra. But with practice, I got better. And you will too. I believe in you. I think you're amazing. So keep up the good work. I hope it all goes well for you. And maybe let's see each other on the other side. Bye.